We are rolling. Hey everybody, my name is Mike Waite. This is the OpenShift Commons Briefings Operator Hours. And I'm going to do what I always like to say is I'm going to share my screen and introduce to you Hazelcast. This is the technology overview from Hazelcast today, and we are fortunate enough to have with us Scott McMahon, the technical director for the Americas. Scott, how are you today?
I'm good, Mike. Thanks for having me. I'm doing pretty well.
Excellent, excellent. Now you're at Hazelcast. Tell me about you. Let's find out who you are. So you're the technical director for the Americas. What does that mean? What do you do with the company? Why are you so interesting? Why have I read so much terrific material about you? We need to know.
Now that's a setup. So I run our field engineering team in North America, and I am the technical liaison that works with our partners, such as IBM and Red Hat and others, to make sure that our technology is implemented correctly. We work with our customers and use things to get the most value for for the software that people buy from us. So I came over. So a little bit about me. I started my career as a software engineer in Silicon Valley a long time ago. But I guess I've always been involved in analytics, and I've always saw the capability or the possibilities around what these computer systems that we were building over time, going way back to doing websites and things, what we could actually do with them. So I've kind of followed my career through from ESBs and message-based, all that kind of thing that we did through BPM and the analytics space. And now I've kind of come full circle, and we're back to actually doing what I think of as business processes, but doing it at a real-time sort of speed and using all the in-memory stuff, but also applying the technology for doing the analytics and being able to understand what's actually happening out there. So that's kind of my whole circle.
When you said way back, what does that mean? I mean, I'm 24 years old. When I think way back, I think like Teletubbies and Blue's Clues. You're probably not 24 like me, of course, but like, are we talking way back? Are we talking VAX, VMS? How far back is way back for you?
A little bit, like back when the internet was something for academic people and nobody ever heard of it, and we were all using links, and this Tim Berners-Lee came up with this thing called World Wide Web, that he called it, and just following that from news groups on Unix systems all the way up to now we're doing e-commerce and shopping carts online. So from the beginning, really.
That's interesting you brought that up. I remember sitting in some college class at some point, and the instructor was like, okay, well, so here's your assignment tonight. And then he wrote something on the blackboard with chalk, and it was like, 8793220 blah 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 at something. And he's like, for any of you who know what that is, you can send your homework assignments there. And I was looking at it, I'm like, I have no idea what that is. So I'll just do it on paper and I'll just give it to you tomorrow. But yeah, that was like when, email was like super rare too. So.
Well, it's funny.
By the way, I'm not 24. I lied.
I remember going down the road and hearing people say, "Oh, you're going to be able to surf the internet while you drive down the road with a device in your hand," and I just thought, that's nuts. There's no way that's going to work. really did a lot of good work. We enabled a lot of high speed. We were all about performance, a lot of financial stuff, and that was fine. We went along with that for quite some time. Now, starting about 5 years ago, maybe something in that range, we, along with everybody else, really started seeing the shifting of how that the data that our systems were ingesting, like how are we getting this data and how are we processing it and the things that we do with it. And it was changing. You couldn't just load it into a storage and then come back and do some analytics later. You had to really react in real time. When you start talking about, mobile devices, like we were talking about, multiple, massively parallel systems, and you have to treat those as individual streams, but at the same time, you want to get that sort of macro layer over the top and see, what is actually going on with my in my environment. So that's where we started looking at stream processing and going back, talking about saying, going way back, we tried to do this 10 years ago or 15 years ago with the ESBs and the BPM solutions, the business process management and monitoring, whatever they wanted to call it. But the systems just couldn't keep up. Now, with the in-memory technology, we realized we actually did have a system that could do this. So we can do 1 million events a second. We can actually look at all these individual events and process them. So that's where we started thinking we have the perfect base in-memory storage solution, but we need to build an engine on top of it that can actually handle this kind of workload that we're seeing. And that's where we started building the streaming engine that leverages the scalability and all of the underlying in-memory technology, but can handle these new workloads, these new things. When you talk about sensors, you talk about industry, you talk about mobile devices, they're always on, always connected, always sending things like GPS or whatever, and you've got to deal with that, and that's what we set about doing.
Yeah. So 1,500 people, 800 people, 10,000 people. How many people at Hazelcast?
About 120 at this point, give or
No
take.
kidding.
We're still pretty
No
small.
kidding. That's
Yeah,
cool.
just a couple of years ago it was 80. We're growing. I think as our customers or our user base really starts to see, they start to experience these things that they need to do. Like, how am I going to handle this? We're growing fast, and there's a lot. It's really fun. I'll just say that, because like we're doing things where, some of the top companies in the world, we get to go work with them and enable them to do what they're doing. I can't really mention all the names because, I don't know who I can actually refer to, but most of the top companies are using us for something or another, and it's
Yeah.
fun to be involved in all that.
When I started at Red Hat, it was in 2002, and there were 260 people in the company worldwide. Worldwide. So I remember what it was like working for a small company like that, where, man, I was a solutions architect and I had like salespeople that I was supporting, and it was like flying to Florida for a 1 hour meeting, then flying over to California, sleeping, taking a meeting in the morning. And I've said this before in the show, but like I remember what it was like trying to sell stuff back then, because we were spending more time trying to convince people like about open source. And we'd go into like a big bank or something, and you know, um, they were like, well, you got to explain to me this open source thing, and how come you guys don't have blue hair and skateboards, right? Don't you're all buzzing around the office on skateboards? And it was like impossible to sell our product, which at the time was Red Hat Linux 9. This was before we came out with our enterprise product. And, we just spent more time trying to defend open source to, well, why should I pay you for something that's free? I remember, being in not Goldman, Morgan Stanley. We're up in the, the 99th floor or whatever in New York City. We're in a boardroom and everyone's sitting around the table with like bottles of Poland Spring water, right? And Birnbaum goes to me. He's like, well, okay, great. So you guys have presented your technology, blah, blah, blah. Why should I pay for something that's free? And I looked at him and I was like, what do you got in your hand? Like, you got Poland Spring bottled water. And everyone in the room was like, yeah. I'm like, well, why didn't you just grab a couple 5-gallon buckets and, go downstairs and go to the Hudson River and fill up your 5-gallon buckets with water from the river, bring it on up here and serve it to people. And that was our first multi-million-dollar deal because they got it that, like, yeah, your technology is open source, but it's just like water. It needs to be refined, it needs to be packaged, distributed, marketed, and frankly, if someone gets sick drinking your water, that you can get taken care of. So that's my long diatribe of what it was like way back when. What kind of challenges do your people see out there, given that you're a fairly young company, and we're going to get into the whole AI, ML. Is AI real or is it a foul? What does it really mean? But like, what do you see out there today that you're hearing from your reps when they're talking with customers about, what the challenges are that the customers are telling you, and how you folks can respond to that?
Funny you say that about the open source. I was using Red Hat back then. I remember that
Which
back in
ver
5. I think the first one I remember really getting into was 5. But yeah, it's been a while.
So just, let me just, hey, it's my show. I can talk about whatever I want. But I remember Red Hat Linux 5 was when I was working at DEC, at Digital Equipment Corporation, and Red Hat sent
True
some people
64,
up
yeah.
from Bali. What's that?
True 64, right? Back
Yeah,
in
True
the deck days,
64.
yeah.
Yeah. But Red Hat sent a couple engineers up to our office here in Mass to make Red Hat Linux 5 work on the Alpha platform. So they ported
Hmm.
Red Hat Linux 5 to run on Alpha, and it did, and SUSE did the same thing, and Debian did the same thing as well. But Red Hat Linux 6 was like the big one. That was the one that like really started to really kind of become mainstream and was in like stores and
Yep.
boxes and Best Buy and stuff like this. But anyways, I didn't mean to steal the microphone from you, but I remember that very fondly.
Actually, it's funny you say that. So I have a question for you. How do you say SUSE? Is it Susie or SUSE? My European colleagues
I
say Susie.
No, it's not, I know exactly why. So when Red Hat came to get Red Hat Linux 5 running on the Alpha, about a month later, the guys from SUSE came from Nuremberg, and it was Jürgen Geck. You can look him up. He was the CTO of SUSE, and it was Jürgen Geck, and he was like a rock star, man. I was like there in a lab, with machines everywhere, and bricks of stores, and like Jürgen walks in with like 4 or 5 engineers, and it was like this electricity in the room. It was like, I don't know, like John Travolta just showed up. But I spent 4 or 5 days with them when they were porting it to Alpha, the initial one, and it's absolutely pronounced SUSE. This is
All right,
from
that's the way
this
I've always
from
said it, but
this is
yeah.
from the CTO of the company, and I don't know where Jürgen Geck is these days, but he was the original CTO of SUSE. And I went out and took him out to dinner, and we went and had, a beer or two, and like I can tell you emphatically that it's pronounced SUSE.
There
So
you go. I have the definition then,
yeah.
straight from the horse's mouth. So no, going back to Hazelcast, what you were asking me, I think it's funny because the in-memory data grid part, that was all about performance, and that was, in my mind, a tactical solution. You were dealing with people that were already building their applications, they're building microservices, whatever they're doing, and they just needed to make it faster. They needed to make it better, but they already had this, so they understood the value. When we start talking about some of the newer stream processing and the event processing that we're doing, that's more of a strategic type of conversation where you have to lay out and make people understand this is the benefits of doing this. This is the business value. This is what you're going to get. You're going to get new ways to do things that you don't know about yet. And it's going to give you advantages or even just handle the problems that you're having that you don't know yet that you even have. So the conversation moves strictly from tactical, how do I make this thing faster, to a more strategic, what is the value and what am I going to be doing in the future as these things grow? And we're only going to see it grow more as 5G rolls out. What are they saying? That's 40 gigabytes per second. Like it's orders of magnitude more. So that just gives developers of apps and sensors and all these different things more bandwidth to work with. And ultimately, all of that comes back to somewhere that you have to handle it. You have to process it. You have to be able to do
Yeah.
something with it. So,
So
that's the conversation that I tend to have more and more.
yeah. So let's talk about Hazelcast. Like when we had our intro call with you and your team, was it last week or maybe the week before? And I was like, don't take this the wrong way, no offense, but like I had no idea what Hazelcast is. I mean, my team's responsible for working with third-party software vendors to help them get their products tested and certified on the Red Hat portfolio, whether it's Linux or Ansible or OpenStack or our storage platforms or OpenShift or whatever it is. But like is Hazelcast the company name? And is your product also called Hazelcast? So I see a lot of companies these days where the company name is the product. And like unlike, Red Hat, we're a company and then we have products. It's like Red Hat Enterprise Linux or OpenShift, but you know, how do you folks deal with that? Is Hazelcast and the company the same thing?
It was. When we were the data grid and the caching layer and all of that, when you said Hazelcast, you could either be talking about the company or the product. It was just Hazelcast. When we started building the streaming engine on top of it, we originally really saw this as two different things. So even though it's the same application, the stream processing engine is leveraging all of the underlying in-memory data grid technology. We sort of divided that and we called it Hazelcast Jet. And then we renamed in a very creative fashion the in-memory data grid to in-memory data grid, IMDG. So we had Hazelcast Jet and Hazelcast IMDG. They're very different capabilities, but they're the same application. But it was a little confusing and it was a little sort of just inelegant, I guess is the best way to put it. So we're actually pretty excited now with our version 5. We're having a major version come out in the fall. We're pushing that all back together. We're putting it all into one application, even though it really kind of technically was. And we're going back to just saying the Hazelcast application. And it will have the stream processing capabilities. It will have the in-memory, the storage. What we think of as kind of data at rest is the storage, and data in motion is the stream processing. And it'll all just be capabilities within Hazelcast. So we'll go back to just being able to say Hazelcast. And that makes it a lot easier. And it doesn't make people choose either. Like when we divided it and we had the stream processing engine Jet or the in-memory data grid, it sort of made people have to decide which one do you want to go with. And I think it sort of clouded the vision of it all. So now it's just capabilities, same platform, same thing, one application. We're a Java application, so it's a single jar, no dependencies. You just run it. If you start 10 of them, they'll all join together and create a big one. If you start one, it can run on a Raspberry Pi. Actually, it's a 15 meg.
So,
jar
let
file.
me ask you this: if I had to describe, Red Hat's products, I would say, Red Hat makes Linux. Linux is an operating system that allows hardware to work so people can, do computing. OpenShift is a container platform. Red Hat Storage is a storage subsystem. Red Hat's KVM is a virtualization technology. What do your products do without like the soup? Like we're gonna get there, but like without the super deep detailed one, just give me the one sentence thing about what it is, because like you can't find that on most companies' website. They
Right.
dive right into like the who, the what, the when, the where, the why. It's like, what is it?
Hazelcast is an all in-memory platform for high performance processing of data. I mean, in a nutshell, we're all about high performance. We're all in memory. We process events, we store events, store data and all that. But in a nutshell, we are an all in memory platform for extremely high performance data processing, if you want to put it that way.
Okay, good. Well, great. Thanks. No more questions, Your Honor. I need to, I'm writing this down. how does all in memory, like I get it if you have like one computer, like you got a 3U server or whatever with a couple sockets in it and stuff, and the memory's there local. How do you do in memory in multi-cloud? I mean, that
That,
sounds to me like magic.
yeah. So from the beginning, that was an original sort of requirement for the design is it had to be scalable. So Hazelcast, you start up one instance of the application. It starts up, it runs, okay, I'm a Hazelcast node. Now, there's discovery mechanism. If you start another one, and it's flexible, you just configure it, whether you're on cloud or on premise or in containers and Kubernetes and the different things. But you start up another one, they will discover each other, and then they pool up their resources, both RAM and CPU resources. So the memory is handled in a partitioning scheme so that as you add more instances of the application, more nodes, if you want to call it that from a cluster point of view, you grow your available storage and you grow your distributed processing. So we have built over the years, the engine of that handles all of the hard part around the distributed processing. How do I run in parallel? How do I coordinate? How do I do my locking and synchronization? All of those things. As a developer, you don't have to worry about it. You just write it as if it's a single application, and then the system handles all of the complex part about how to do that. So the idea from the beginning was that it had to scale. You had to be able to add more resources, gives you more storage, gives you more CPU, and there's theoretically no limit. Now, ultimately, you're going to run into like a network bottleneck or saturation type of issues, but we've got hundreds of nodes running with terabytes of data and massively distributed. When you write an executor or a processing service, the system runs that out in parallel, understands how the data is distributed, and then it's similar almost to MapReduce. We're not really like MapReduce, but it'll run and do various things in parallel and then kind of shrink back and then ultimately give you your answer. And the stream processing engine does the same thing. It figures out, you define your process of what you want to happen or how you want to handle these events, but the system takes it and distributes it out across all of the available resources and uses all of those resources because we want to get the extreme high performance as much as we can get. So we're going to use all the physical resources to be as low latency, as high throughput as possible. But all
How do
that's done for
you,
you. The engine that we built handles the complexities of that.
so by the way, we are live on YouTube and Twitch and Facebook and a bunch of other places right now. So if anyone has questions and they want to basically, what I like to call Stump Scott Wednesday, drop them into the chat down below, and then our bots will magically make them show up here in our little bridge. But it's officially called Stump Scott Wednesday. My question
I
for
like
you
that.
is like, huh?
I like that.
So
I like that.
yeah, but um, how do you maintain state? Like before Red Hat, I worked for this company called Mission Critical Linux. No one's ever heard of it. We ended up getting bought by Red Hat, but we were building something called Convolo Data Guard, which was high availability clustering for Linux, and we required shared storage, and in the shared storage you could have multiple nodes. There was like a quorum partition where the different nodes would vote about who has state. And so you had to have at least three so you didn't get a split brain. Like you couldn't have four
Mhm.
or two or something like this. That's probably like super old technology. Anyone interested, you could probably go Google Convolo Data Guard. You probably wouldn't be able to find mission critical Linux anymore. But we became Red Hat. But whatever. How do you do that in multi-cloud? Like where is state maintained if you've got nodes all over the place and you're doing shared memory? Where do you maintain state?
Mhm.
Um, and how is
So
how is it done? And isn't that a huge performance bottleneck?
that is a very interesting question, and it's something that we definitely have to deal with. There is, if you've probably heard of CAP theorem, CAP, and that's where you get into the differences between availability and consistency. So yes, we have to deal with that. We have simple quorum, if we wanted, if it, depending on what the SLA, what the use case is. So we can do simple quorums that for most common use cases is sufficient because it prioritizes availability over consistency. Now, if you get into use cases where you do have to require a ironclad level of consistency, we've actually implemented the Raft protocol, if I want to get into those kind of details, so that we can have structures that are shared that guarantee consistency, make consistency guarantees. So that is an issue, but we have given choices, and you can pick. Consistency does come with a performance impact. So as a user, you can pick which one, whatever your use case is. Now, I will say too, the interesting part of that, and for us, a strong suit, is that we were originally a storage layer. So we had that distributed, managed, all of the engineering to do that storage and locking. We have fenced locks and different types of CP locks and all these different types of things. We had that in place. So that put us, with our stream processing especially, in a pretty unique position because we can store. So we can store state. And one of the things that we are beginning to roll out now, and we've been working on for quite some time, is a whole new way of handling the contractual type of concepts for microservices, and when you link those things together. And if you've heard of a newer concept, instead of doing transactions, we're actually doing sagas, if you will. That's the new kind of way to do it, where you wrap things together, and then you have automatically compensating for failures, no rollback and do these things. But what that's going to give us is a way to handle the microservices type of architecture, where you can put things together and wrap them in a saga, and then if something goes wrong, you roll the whole thing back. It compensates for itself, but it gives you sort of a transactional nature for multiple, what is the word? When you put a bunch of things together, I'm forgetting the word, and be able to handle that. So it is then stateful microservices type of architecture, and that is because from the beginning we've had that storage layer, so we've had the ability to do this. Whereas a pure stream processing engine probably doesn't have the storage layer, and a pure storage layer probably doesn't have the stream processing engine. So we bring both of those things together, and you kind of end up with the best of both worlds. And again, I'll hit it again, it's all in memory, high performance. We actually, on that same lines, we were doing some scalability tests just a few months ago, and we've got a blog post out, and we worked with some of the academic institutions that have a standard type of testing for throughput, and they have a certain set of queries and transactions that you have to handle. And we wanted to see how well we scaled, and we wanted to ensure that linear scalability, so that as you add more resources, you'll see more performance and you don't hit that kind of hockey stick thing. And we were doing 1 billion events a second in our transactions, and it's no one's ever done that before that I know
That's
of.
that's pretty good. 1 million transactions a second, Scott. That's pretty
No,
good.
billion, B with a B.
I know.
But we only stopped there. That was 45 nodes, and that was running up, I believe it was on AWS or one of the clouds. I don't remember which one it was, but we stopped there, and there was no limit. We could go further, but it just seemed like a good round number. So we stopped there and said, all right, we did a billion.
What does it do though? Like, what do you get? You're doing a billion a second of, like, what does that mean? Like, if I'm a consumer, and like, how does that benefit me, a customer? Like, a billion what? Like, what, like, okay, great. I mean, a billion, requests, a billion messages, like what is it?
So I was kind of thinking the same thing when we caught that out. I thought, well, nobody has a billion events a second. We do a lot of credit card transaction processing, and we do fraud detection, and we apply all this stuff. And I
Yeah.
think really, even with the largest, we pretty much most credit card transactions touch Hazelcast in some way. I don't know who I can name or not name, but even the largest one, like I know I can say Capital One. They use us for their fraud detection. They might do 30,000 a second, something like that. So these use cases, I thought, well, it's just a fun kind of academic thing, really. But
Yeah.
now, actually, now that it's come out, there are so there's some streaming video processing sites that you go to watch movies and things like that, they do have billions of events a second in their events. These are requests, replies, searches for movies, whatever the command to start the streaming sort of thing. They really are. They're worldwide, and
Yeah.
they are using us now and testing for use cases we've never seen. So what it gets you as a consumer is that whether it's a mobile app or a web, browser or an application, it's going to perform in what I think of as more like human scale, where you click on something, you want an answer. You send a query, you don't want to wait. It shouldn't take 10 seconds and then finally come back where did I click it right? Maybe I need to click it again, and then you open two things. You want to have real-time interaction or the ability to process these events in the time frame that is important, basically. And as we say, events lose value with time, and certain things happen, and you have to react immediately at that point. And if you don't, then you just don't even bother. You might as well not even bother. So, from a user standpoint, it gives you the ability to handle the workloads that we're seeing with massively parallel streams and individual, and the ability to react to those, and then also have a big picture of what's going on in my world, and am I performing right, and am I meeting the needs that I said I was going to do. So it's kind of, it's across the board. It depends on if you mean your user satisfaction, or do you mean the ability to react in a time frame where I can make money and take advantage of the situation, provide a service that I wasn't able to provide before, those types of things.
Hey, I didn't ask you where is Hazelcast? Is it like a California thing? Are you guys Israeli? Are you from Bogota, Colombia? Like where's the company headquartered out of?
We truly are a global company. The original founders were actually in Turkey, but the company, they came over to the U.S., incorporated in 2010 in Silicon Valley. So we're Palo Alto, San Mateo now. We moved from Palo Alto to San Mateo because our office was too small, so we outgrew that. But we're global. We have still a large engineering team in Turkey. We have some in London. We have some, a lot in the U.S. We're everywhere. I'm located in Portland, Oregon, actually. So we're truly a global kind of virtual team. But our headquarters is in California, in
So
Silicon
you're in
Valley.
Portland, Oregon, so you're getting the same heat wave I'm getting here in Massachusetts. It's like
Actually,
100.
it cooled off today. Yesterday was 115, and the day before that was 112. It's never been seen before. This is just like, I don't know. It's almost something out of a movie. But
Yeah.
today it's only mid 80s. It's cooled off
Well,
again, and it's like mid
it's
80s.
103 degrees here. It's 100, excuse me, 106 here, just north of Boston. And I went to turn on my air conditioner for the first time in 2 years because usually I don't need it, and it was out of Freon because there was a leak in the line. So thankfully they were able to come and fix it. But
Well, I
um,
had the opposite experience there. I got recruited up there in Cambridge, and they brought me up in the spring when it was beautiful. Oh, look, the St. Charles River. They're out rowing. People are running. It's beautiful sunshine. And then the winter hit, and it was just like, I didn't know that whole river froze over. It's like, my God,
yeah,
that was freezing cold.
yeah, it
So,
freezes over now because it's actually getting pretty clean. But it used to it used to never freeze because of all the junk that was in it. Um, Hey, you were talking about containers and you used the word microservices. If you talk to any company that makes like a service mesh, tool or offering like that, it's like microservices, microservices, microservices. And everyone's all like, this is where it's going to go. You got to have a service mesh to manage all these things because the containers are getting so tiny and the, 50, 90,000 of these things. But, when I talk
mhm.
to some people, they're actually saying the containers are getting bigger. how
Yeah.
how how does the number of containers and the size of the containers affect the ability of Hazelcast for doing distributed, stateful memory across nodes?
Yeah,
I'm still on
that's
the
actually a
Stump Scott Wednesday challenge.
that's actually a very common use case for us, and the reason is that especially if you're a Java technology, since we're Java, you can actually embed Hazelcast directly in your service, and if not, you can use a client. And we say that we're polyglot, so we have clients that talk to the cluster and all of the major languages. So either way, what we typically are used for is that we provide a very easy common data storage access layer. So, and all of that is shared in the microservices. So if one microservice does something that inserts data or modifies data, that's immediately available to any other microservice on a different container that might call into that and fetch that data or request that data. The way we do that is that memory partitioning scheme, because what we say that our nodes or our clients are smart, and what that really means is each one of them has the entire memory mapping partition map within it, so it knows exactly where every piece of data is when it goes to get it by the key. Now, where that's important is because as you scale and you get 100, 200, 1,000, different instances of these services, the data access time and latency will be linear because it's one network hop. So you don't have to go from one to another and go find something. Everyone knows exactly where that data is. So when a request comes in, even if it's 3 nodes or 300 nodes, it's still one network hop across the switch, gets the data, fetches it back. So you can theoretically grow as big as you want and still have that linear, consistent access time. Now, as far as the containers getting bigger, yes, they are. I agree with that, but that's just bloat. That's just people not really building those containers as lean as they want. I've seen some of them get to be, a gigabytes in size, because, or not gigabytes, like terabytes in size, because
Right.
not terabyte. Well, just big, because everybody's,
Pretty
oh, let's just
darn
stick it
big.
all in a container. Yeah. And it's
Yeah.
too big. That's not what they're made for. And that's just, we can do our part and give fast access, but ultimately, a lot of that container bloat is just around discipline of your development processes. But we do give you the easier way to handle all of that back data plane, and you don't have to do it yourself, because that's the hard part. Consistency. How do I access the data? How do I guarantee the changes are reflected immediately? All those types of things with parallel and concurrent systems. That's what we built. So we built that engine to handle all that. So all you really have to do is say get and put, and that's it. You don't have to worry about the details.
So what about public cloud? There's a lot of companies out there. I forget everyone's doing studies on resource allocation in public cloud, and a lot of the reports that I've seen from companies, I don't know if I can name their names, or are that basically when customers are running workloads in public cloud, they're over allocating resources, like in a big way to like does does Hazelcast help with that in any way to allow customers to not have to over allocate resources in a public cloud, or do you guys just exacerbate the problem?
Well, I hope we don't exacerbate the problem. I think we do. We would help because we offer that shared data plane, and you can be much more concise in the data that you store, and you don't have to have copies and make distributed types of things. Now, on the other hand, we do enable easily, add more containers because we make it very easy to do. So again, I don't think we either contribute or exacerbate it, but we do give an easy shared way to store and access data in a high performant way. Again, I think you just go back to kind of your engineering discipline, in that you need to have a good plan and make sure you control your resources. But I think Hazelcast would give you, actually, now that I think about it, it would probably help you with using less resources, because you wouldn't need to add a storage layer. You would have Hazelcast directly in your applications. It's shared. It can grow and shrink independently of what your applications are, depending on your storage needs and your processing needs. But it could be more concise and tighter on the storage. But again, you can have the best tools. It really comes down to adhering to your discipline and engineering best practices. But I think we could help.
Okay. Well, that was as close as I can get to Stump Scott Wednesday. Um, when we were talking before we went live, and by the way, we are live. Hello, everyone. You said something about like the terms AI and ML, AI and ML, AI and ML. Oh, we do AI and ML. This has like been like the buzzword bingo for at least 3 years. And you said something when we were talking before, the camera went live that like AI, what did you say? We were talking
Science
about machine
fiction.
learning. What?
I said it's like science fiction.
What is
Everybody
that?
uses the term, and
That is a pretty provocative thing that AI is science fiction when so many companies out there are all saying that they do AI. So how do you defend that statement?
true. And I probably, maybe that's not the right way to say it. It's not science fiction. It's actually really there. The question is, how do you put it into production? How do you actually use it? So when you start talking about AI, machine learning, these different algorithms, you go all the way back to the 60s, in the labs at the colleges. They were developing these algorithms and these methods for doing intelligent type of decision making, but it was stuck in the lab. You couldn't get it out of there. And I would say in like the last 10, 15 years, now you have companies that are coming out with tools that mean you can build models, you can build these machine learning models, and you don't need a PhD in data science to do it. You can, they're automated. I don't know who I can mention, but like H2O and Data Robot and all these guys, they're giving the tooling for the average person, just an IT person, to be able to build these models. But then you still have the problem of, how do I use these things? How do I put them in production and make them valuable? It's like, yeah, it's cool technology and all that. So that's where we are focusing. We're building with our streaming engine. If I can go a little bit into the technical details, we built it on the concept of a DAG, a directed acyclic graph. That's what Spark uses. It's a pretty easily proven type of technology to control and manage the process that you're building. But we want to enable the injection and usage of these models. We're not trying to be a data science tool. We're not trying to be a training tool or anything like that. We just want to say, all right, you go build your models in whatever you want, whether it's Python, C++, or Java. But those are the kind of the three main. You export this model and we will ingest it, and then we will call it and we will run it. And that's where I was saying the science fiction idea is like, and that is pretty provocative, but it's really like, you can talk about AI. Everybody talks about AI. They just want it on their web service. It's like blockchain, just get it on your website so that, you can get robot
Right,
hits or something.
right.
But how do you actually put that in production? It's there, but how do you use it? And that's where we really saw ourselves as being able to implement this and be able to run these things in production, like fraud detection on credit card scores. We're doing that. We're actually, we have most, like I've said, most credit card transactions touch Hazelcast in some way. So a transaction might come in, the user swipes the card. Generally speaking, you've got a 1 second SLA from card swipe to either approval or decline. And that's going through all the network, goes through the processor, goes all the way to the issuing bank. The bank issues the money, comes back. That's that whole thing. So your fraud detection, generally, you've got about 50 milliseconds to pull that off. And what we've seen that we could do with our models, and not just data science models, you can do rules engines and some other things, but we can actually apply more and get more accurate scoring results in less time using the stream processing engine and being able to enable these things in real time. That we've seen tremendous benefits. I think I can use the Capital One example in that they saved something like $100 million a year in not only just detecting better fraud and declining fraud transactions, but also false positives, not getting false positives. Because if you score something as fraud and it's not, and you deny it, then the user is just going to pull out another card and use it. So you've lost that revenue. So you've got to
Yeah.
have a better way to detect fraud and also not make mistakes in declining. So that's what I talk about when I was saying it was science fiction. What I really meant was everybody says they can do it, but nobody's really doing it yet until now. And I think we're doing that now.
Okay. Now, you guys have been working with us. The reason why you're on the show today is not because we think, we think you're nice and we like your flower arrangement there on your bureau in the background, but our engineers have been working with the Hazelcast team for quite some time, um, to test and certify your solution on Red Hat OpenShift and other products. But let's be realistic. OpenShift is, certainly, the one of the future technologies for us. Your software, you've built an operator, which is sort of like an artificial intelligent agent for managing and orchestrating your technology along with OpenShift. You folks are in the Red Hat marketplace. People can go to the marketplace and buy. You can download your operator from our registry. And, I just wanted to throw a plug in there that this is all about, improving the supportability, the day two supportability of for customers when they want to use, your products along with ours. That was just a gratuitous plug there for us. We have 11 minutes left, and I know that, people probably are like, what's the architecture look like, Scott? Like, how does this work? Like, it's great, you guys haven't been, delivering death by PowerPoint, which frankly is really refreshing. But I didn't know if you wanted to put up that architecture chart there that we were talking about earlier.
Sure, I can. It's not really necessary, but I will put it up. Let's see. Let me share my screen here.
Don't you wish that all the various different video chat things had the same way to share a screen so you didn't have to hunt around for them?
Yeah, well, maybe one day, but as it stands, I like competition. Some are better than others. So, we have these applications competing. They add features. Zoom added the virtual background. Now everybody has virtual backgrounds, and it's been pretty fun.
Yeah.
So to talk about the architecture a little bit, this is a sort of a conceptual idea of what it is. We are in essence, though, a cluster or grid, as we say. And the reason that's important is because we engineered that from the beginning for the storage. So all they do, they have to just have a way to find each other. So when, say, you have a 3-node cluster running and you want to add a fourth one, when that fourth one comes up, it just needs to have a way to find it and find the other one. So that's what we call the discovery mechanism, and it's configurable. We can run, directly IP, or we interact with all the orchestration engines, Kubernetes and OpenShift, and all the things that you would expect. But once they once they find each other, once the new one finds the cluster, it just opens a direct socket, connects, they share information, the topology is sort of distributed, and then that's it. That's how it joins. And as a client, or however you want to access the cluster, you do the same way. You just open the client opens a socket, has direct access. Since this is the way we engineered it from the beginning, it really fits all of the containerization ideas that have come along later. We didn't actually build this thinking Kubernetes because Kubernetes didn't exist, or OpenShift because it didn't exist. But it fits the way that those scalable resources work, because that's what we wanted to build our platform as. So what you see here on the screen, this is sort of euphemistically referred to as the north, south, west, east diagram. And what it really is that we have that distributed data storage layer, which is what we call memory, or store data at rest, if you will. That's where we're actually putting it into memory. It's highly available, easily accessed, and high speed, but it's stored. And then on top of that, here's the streaming and batch processing in this diagram is the streaming engine that I was talking about. And that runs distributed out across all the nodes. So it uses all the CPU, all the memory, whatever resources it needs to do this distributed processing. So our traditional use case is kind of top to bottom, where you have microservices. They may be using different clients, or it could even be embedded, like I said before, if it's a Java application. But it's generally accessing that stored data, and then there's a configurable connection to the persistent storage layer, which is usually a database, but it doesn't have to be, but it usually is a database. And then that data is loaded and made available, and if there's synchronous needs, then changes are made to the database, or vice versa, back and forth. That's your top to bottom microservices
Let
architecture.
me jump
Hmm.
in. Tell me about the distributed memory first database. Is that part something you offer, or are you saying that you have a requirement for interfacing with a distributed database?
No, that's us. That's Hazelcast. That distributed, that's the storage layer, that IMDG as it referred to, in-memory data grid. That's the base foundation of our application. So everything you see in that middle green box is Hazelcast. That's the Hazelcast
Okay.
application.
How would you
And
characterize like what type of database it is? I mean, and there's NoSQL, NewSQL, MySQL. Is it that kind of a database?
I would say it's mostly NoSQL. And by the way, people think NoSQL means NoSQL. It actually stands for not only SQL. So we are an object store at our core. So we've always been that, and that's because we were about performance. So if you have a normalized schema, then every object access has to be reassembled. And that's why schema-based databases are better for reporting and analytics, and then object stores are better for performance. So, there's trade-offs between the two. Now, we have actually added a SQL layer engine not only on the storage layer where you can use SQL, ANSI SQL, and interact with the objects, and we've built in a parser and all the stuff that you need for that kind of access. But that is an object store. We've also built what we call streaming SQL to attach at any one of the points of what you see there, that graph. That's basically a representation of the DAG I was talking about, the directed acyclic graph. You can attach a SQL query at any point on there and what we call streaming SQL, and then get a continuous update of the events, from a SQL language, but and with a SQL type output of events streaming through. But to go back to it, that entire middle box is the Hazelcast application, and it brings that storage layer, what we used to call in-memory data grid, but now it's just distributed memory database, and then the streaming engine on top of that. That's the Hazelcast application, and that brings all of those capabilities to be available for your storage and your processing.
Okay, well, thank you. Your marketing folks, were sending me emails. They're like, "Hey, got to make sure you can drop your slide down now if you wanted to,
Okay.
Scott." Your marketing folks were like, "Hey, you got to make sure you talk about." Now I'm going to read this because I was trying to, be the good person here. The real-time stream processing, production use of ML, and changing. I'm reading, by the way, and changing data processing needs. Have we talked about that, or we have, a few minutes left here? We need to
Yeah.
pick and choose what we want to make sure that you do to placate your greater marketing team.
I think we have. What they're really referring to is just that the landscape is changing. The landscape of how we're processing data, how we're doing things is going to change. It's not, you can't store something in a persistent storage and then come back overnight and do queries or analytics or whatever the way we used to do it. You have to do it in situ. You have to do it as you're running. If you don't have the performance and you can't keep up with it in real time, storing it and trying to do it later, you're never going to keep up with it at that point. So I think really for us, the way that we're seeing things work has fundamentally shifted over the last 4 or 5 years. And it's just going to continue to grow and continue to move in that direction where you just have to have systems that can interact and work in a real-time manner. You can't wait. You can't store and wait. You just can't do that anymore. So that's really where we see the whole fundamental shift of how things operate, and it's got to be distributed. There was so if you go way back, there was a woman named Grace Hopper, and she was a data scientist in the Navy long back in the 60s. But she always had a quote that I really loved, and it said, back in pioneer times when you had to pull up stumps, the pioneers didn't keep trying to just grow a bigger ox. That you hook up more of them together, and you have a team of oxen to pull out. That you don't just keep trying to make a bigger computer. You have to team them up. You have to distribute, and that's where we see it going, and that's what we've been built to do. And it's only going to continue to get more and more complex and parallel. I mean, you're going to have to take advantage of the parallel concurrent processing to reach the scales that we're seeing now, with the internet and the new things that are happening and these, these devices. I always point out the iPhone 3 came out in 2007. I mean, that you think these things have been around forever, but it really hasn't been that long. And I can't even imagine what it's going to be in 5 years from now.
They,
Maybe they'll just stick them right in our head, I guess. I don't know.
I had a Trio. Do you remember the Trio?
Oh yeah.
It kind of had like a keyboard on it. It was a phone, but it had a full keyboard, like kind of like the Blackberries do, I guess, or something. Or I don't know. Anyways, you're right though. Phones certainly have. I just hope they don't keep getting any bigger. I don't want I don't want to have to wear a hip holster to carry a phone. Like,
Yep.
I mean, I work with hundreds of, propeller heads, and they're all walking around the building, and then they're like, "Oh my God, I can't believe you haven't rooted your phone." I'm like, "Dude, I don't want to root my phone. I want to be able to
Yeah.
text and make phone calls, and I don't care about rooting my phone." Anyways, we are out of time. Um, so would love to have you back again. I don't know if you guys have been part of our podcast series that we do or not, but you should. I think this is a really interesting topic. And if you folks wanted to come on to our podcast show sometime and talk, at any level that you want. If you want to bring like some of your engineers on there and they can, talk about, hashing files or whatever, but you're more than welcome to come. Um,
Sure. That sounds like fun.
yes. So what's
Always
next?
willing to talk about it.
Yeah, I gathered that. I get the sense, remember when we were doing the dry run and I was like, all right, Scott, now listen, no one word answers. We've got an hour. We got an hour. We got an
And I
hour.
said,
So
okay, that's
yeah,
two.
yeah. All right, great. Well, Scott McMahon from Hazelcast, thanks so much for joining us. If anyone wants to get in touch with Scott, how do they do that? What's your home
Well,
phone
my
number?
email's scott@hazelcast.com. You can get me there.
Scott at hazelcast.com, and I'm Wait at redhat.com. So thanks for coming. Thanks for being our victim today. It was enjoyable.
Yeah, it was fun. Thanks for having me. Appreciate it.